This lecture starts a block of lectures devoted to search in multimedia databases. So we are now focusing from the general web environment to multimedia data. We started with texts, then continued to graphs. We also mentioned semantic web technologies and formats, and now we go to multimedia. Why we go to multimedia? Because the multimedia content now basically dominates the volume of the space of the web space, and it is also the subject of many applications that today are dominating the web, specifically social media applications and hosting servers, streaming applications, and so on. The introductory talk today is a kind of overview talk that then in master studies continues with standalone course that is called Similarity Search in Multimedia Databases or Multimedia Retrieval. And as the title suggests, there are some specifics about the focus, and we can visualize these specifics by this diagram. The main area for this topic is information retrieval, but not the full text search and not text retrieval, but multimedia information retrieval. There are many questions that are inherited from the text retrieval, but there are also completely multimedia specific problematics. Because there will be needs for extraction of information from multimedia, and the multimedia is audiovisual content mostly, then we will also borrow some techniques from computer vision and computer graphics. There are also questions of scalability within multimedia information retrieval, so we'll also look on techniques from database systems, mostly indexing. And of course, because we are still in the web environment, there are still relevant techniques for web search engines, and we also need some expertise on data modeling and descriptor modeling for multimedia, so data exploration and data management topics are also relevant for this block of lectures. So we are moving somewhere here in this overlap, and as I said, these 5 lectures will be, or some of them, for 4 lectures will be devoted to topics that are in more detail discussed in these master courses that are fully focused to multimedia retrieval. Okay, so what's the motivation? Again, I start with motivation. We can expect that more than 95% of the volume of web space, I mean volume in the bytes, in the measure of the data volume, is considered to store multimedia content. As I announced, the mainstream services that deal with multimedia are nowadays social media, social networks, hosting servers, streaming servers, and so on. For example, there is expected that every minute there is 500 hours of video uploaded to YouTube every minute. So this is a huge loads of data. Or it is expected that hundreds of billions of photographs are taken every year and uploaded to social media. So we really experience a huge amount of multimedia data that is produced by ordinary end users, and that somehow upload the content on the web into web services or web applications that maintain this data. The factors for this, what happened? We started with the basic web infrastructure, only with web pages or linked web pages or the web graph. But during the time there were developed also web applications, and some of the applications started to share or host multimedia. And with the beginning of new millennium, this began to be extremely dominant trend in usage of social media and other services. The factors are that in the first years of new millennium, several factors came together. There was high-speed internet available at that time. Finally, also the computational power of common computers or devices increased to the level that it could actually store and play multimedia videos. A few years later, the onset of cheap digital devices appeared. So maybe 5 years in 2005 or 4, the digital cameras massively became a standard for end users. Even later, smartphones. So during these quite a few years, the situation and the landscape of web changed dramatically, and everybody became a producer of multimedia data, and every producer of multimedia wants to share the content, and the motivation, of course, is to put the content to some sharing or media sharing environment, such as social networks. At the same time, human activities moved in large extent to internet. So it is the same period for boom of e-banking, e-commerce, and so on. So we are now looking back 15 years back to the massive start of multimedia on web within the applications. Okay, so what is actually a multimedia? What's the definition of multimedia, of the word? Well, there is not one exact definition that is just one. There are many of them, but we can use the very basic and traditional interpretation of multimedia, that is something that more than one type of some digital media, and in the traditional interpretation it means we are talking about image, audio, or video content. So in short, it's about audiovisual information, audiovisual data documents. In some extended interpretation, we could also take into account other kinds of digital formats, and they basically are based on the way these data are created. So mostly it's sensory data, something like digitized nature. It is also the case of audiovisual data, because we have sensors in the cameras and DAC converters and ACD converters. So we can really capture the signals from nature and digitize it, and that's basically how we get multimedia. And not only multimedia, in the broader interpretation, it is basically unstructured content, because these low-level data coming from sensors have very low-level structure and semantics. In case of images, for example, it's just pixels, and the metrics of pixels is suitable for storage or for reproduction on display, but it's not suitable in this form for searching. So this is something new. We need to process this data differently than we are used in other types of data. We also can get unstructured data by other means than sensors. We can have human process data like of course the text. We already discussed text and models for text retrieval, vector model, Boolean model, and text is also unstructured, but at least it is it has some semantic, some basic semantic in the words, in the keywords alone, because we mostly have texts that are defined on top of some natural language. So we don't have artificial text. We have text that are somehow anchored to natural language. We can have also other human process data like geometries, maybe also applications on internet. We can really extend this to many different forms of the data types. To imagine what I mean, let's overview the producers of multimedia data. So most people would imagine the individual producers of multimedia data. So the end users, the mainstream or massive group of multimedia data producers are individuals, basically free time users. So, and this is what we in these massive numbers observe on social networks. These images basically are images, leisure images, some free times activities. There are not much multimedia that are intended for some critical usage. So as these three examples, these data are not some critical data that must be communicated to everybody. And also when searching for multimedia in this domain, which is very general, there is probably not expected some extreme precision of searches for this kind of data, because nobody dies when I don't find this cat. So the use case is really free time usage. But we can have also producers that are not so easy, like in industry and research. So in industry, we have critical use cases for searching multimedia data, because for example, we can have a sub-branch of imaging or representation of human features in order to authenticate or to identify people for different reasons. And for example, we can have photographs of faces, photographs of irises or fingerprints, and we need to do representation of these kind of objects in order to provide critical application of biometric identification, for example. So this is different case than in the free time users. Also in manufacturing, we can experience 3D models, for example, in automotive manufacturing. There are huge databases of 3D models. Again, this is completely different use case, and again this is multimedia. On financial industry and also in scientific applications, we can meet various measurements in the form of time series. In this case, this is a stock price, but it could be any again sensory data measured in time, some phenomena in time. So this is also not only in industry, industrial sensors, but also in research or in medicine. and so on. So this is something different. Also, these data are not available on web. They are protected because they are not part of some social entertainment, but they are really professional, and they must be preserved. Next is the research, and this is similar to industry, especially, for example, in medical imaging. We can have very many different means of digital examinations and different kinds of images that basically are used for diagnosis. Here we have some ultrasound. Here this is computed tomography. Here we have very interesting data type, which is multi-dimensional time series. This is EEG. We have not just one time series, but multiple of them, and they are all synchronized in time, so they should be taken as one object. This is ECG. And also in other disciplines like bioinformatics or biochemistry, we experience data in the form of unstructured data, in the form of, for example, 3D models of molecules that are not just 3D models, but they are 3D models with the properties that are relevant for bioinformatics or biochemistry, like some chemical or physical properties of the atoms that are attached to the geometry itself. So this is very specific, and the domains are really widespread. Okay, so we have just a bit of notion where these data come from, and now how to basically create a mechanism or a model for searching this data. So we already know the techniques for full text search, and this is maybe the easiest way how to do also multimedia retrieval, to attach some text on the multimedia data. This is called basically the context-based approach, where we suppose there is some external information attached to multimedia data, and we just search using this external data, not the multimedia itself by the content, but the annotation. So this is how, for example, Google works when we are searching for something, and we have different options what we want to return. If we want web pages of OK, we have the page with the window with the web pages. We can, with the same keywords, search for images, for videos, but this is done the same way. So also the keyword query is applied to return images or videos, and this is possible because the indexed videos and images, the multimedia, is described again using the same technique by text, and this text could be used from the web pages where the images or videos are embedded, or so there is a web page, and we have image on that web page embedded within the code, HTML code, and we could use text that is surrounding the image and use it as an annotation, for example. Or it could be even more easier, just taking the keywords from the URL of the image, and this is taken as an annotation. So this could be really easy. And this way we can reuse the technology for full text search also for multimedia search. Okay. This is the case for Google, because the web search engine for web pages is merged with search engine for multimedia. So this is the synergistic solution where we can really use the context of a web page. But otherwise, if we want to search by context, we need some human annotation of the multimedia. And this is something that is really hard to get, because this is some extra activity that must be demanded for annotation. Of course, this is even easier in social media applications, because we get annotation as a side effect of the interaction at social network between people. And if somebody posts a photograph on social network and somebody comments on this photograph, and there are likes on the photograph, and there are other external information, external annotation of this image or this object, we could take it as the context and use it in search. On the other hand, content, this in the case of multimedia data, content means the actual raw data that is basically the pixels in case of visual data, or the audio wave, the digitized wave in case of audio. So if we don't have any context, we just have the content. So the only information we could actually use is just the content. And these are the two approaches that we could use for searching multimedia data. Here we have example from Flickr, where a photograph is depicted, and nowadays Flickr is also a kind of social network. We have user profiles there, like this one. So the author of this picture basically uploaded this picture on, and it is in the social context. So the social context could be taken as the context we are talking about, and we can see here that we can distinguish between manual annotation, basically some manual activity when we want to really annotate this picture, and also some automated annotation that comes as the side effect of the social network. This is the crowdsourcing effect, when somebody uploads object and somebody else is commenting on this object. Of course, these red annotations are more valuable because it is authored directly by the user that uploaded the picture. So for the title, he chose vacation transportation, and the user also entered tags for the image, so we can see from the text that this is probably a picture from some Thailand island. We can see from the web page. On the other hand, there are some comments to this picture, and here there is good job, friend. So this is not much valuable annotation for the image in the sense that it doesn't describe the content of the image. It's better to use this vacation transportation for that. We also can get other annotation data, like the GPS coordinates. Like here we can see that it is really in Thailand, and this comes from the camera, if the camera is equipped with the GPS module, so it comes also for free with the photograph. So this is how can we see content and context. Content is just the image, context is the everything else. Now, if we resort to text-based search, so using the context and relying on the context we get from somewhere, from the social network or from the embedding web page or something, then it has definitely some pros, and the basic or biggest advantage of this is that we could reuse the technology for full text search, and because of this we have also the benefits of high level description, and therefore we could match it to high level queries, because text is the means not only for the queries, for the keywords, but also for the context. So both context and queries are based on keywords, so it is easy to provide some matching of keywords using either just trivial match or using bag of words model by cosine similarity and so on. So this is the largest benefit of text-based search for anything, not just multimedia, but anything. Again, because of the mature technology, we could reuse the full text index, the inverted file we already know from the Boolean or vector model, so we can reuse it also for multimedia because we just index the full text again, but this time it's only metadata for the actual data, the multimedia, but doesn't change anything on that. So this is again the advantage. And with the ever increasing influence of social networks, this trend that everything that is uploaded is immediately equipped by some automatic context becomes even more stronger, because everything now is incorporated within the application platforms of social networks. So the likelihood that a multimedia object that appears on social network gets annotation gets higher and higher. So this is again advantage also for the future. But there are some also cons, some disadvantages. In the classical interpretation, it is quite laborious to create the annotation if we don't use the context based on social networks, as I said just now. Then if I really require some rigorous annotation that needs to be precise and so on, I need really the text that are connected to the object, then I need to hire human annotators. And even if I hire an annotator, it still doesn't solve the problem in its whole complexity, because the annotators are only humans, and therefore they are highly subjective. So for just one image, I can have two different annotations by two different users or annotators. So this is not so reliable. I would like to have this possibility. And also because I don't have the resources to annotate everything, then also the annotation is incomplete. So it's really tough to equip all of the data by some meaningful annotations. Nowadays there are of course advances in machine learning, so this human labor could be replaced by machine learning to some extent by pre-trained models that are able to automatically annotate multimedia by labels. For example, the Google Vision API is able to annotate images by keywords using the Google's pre-trained model for general imagery. But of course, this is not for free. There's some demo version for free, but otherwise it's paid. And mostly this approach is limited by two factors. First, it only works well for some mainstream domains. For example, general imagery, that's the domain of the free time users, where the photographs basically contain people, social situations, nature, animals, and so on. So in this very general, completely very unspecific domains, this works because these models are trained for this data, and there are multitudes of these examples. So that's why they are present in the training data. But so in other completely specific domains, this doesn't work. So for example, if I want to classify, let's get back to this, and I have some mineral, some cut of some stone, and I see something, and I put this to Google Vision API, and I get maybe this is, I don't know, this is stone, but I don't get any other information out of that, or this. I only get very rough classification, and I would like to know the class for the specific mineral that this is. So once we get to very specific domain, these pre-trained models are very limited. And also there is limitation. The second limitation is in the level of detail, which is connected with the domain, because I can have general imagery with some social situation, and I get some classification of objects that are appearing in this photograph, but I definitely do not get all of the objects that are present in the photograph. For example, there are annotations for glass of water, for computer, for chairs, some furniture, but there will be not class for example, a cactus plant, or because it's not in the trained model, and this is again the limitation. And so this level of detail is another limitation. So basically, we can battle somehow these cons for human labor, but it's not automatic, and it's not solve problem for all of the domains and all of the levels of detail. Okay, when we look on different data models where the structure and semantic is strong, and go to the data models where it is loose, we must start with relational databases. Relational databases, from this point of view, is very easy and very simple data model, because it has both strong structure and strong semantics. Because relational databases are just plain tables in the first normal form, so we basically have nicely shaped table where the rows are records and the columns are attributes, and all records have some value in the attributes, because by the first normal form we require there is always value in each cell of the table. So we have complete information for all records to all attributes. We have nicely typed attributes, so every attribute, a part of the name of the attribute, has a type, and the type is simple data type. So we basically know the structure and semantics of the attributes, because they are just one of a few basic data types. And we have also strong semantics, because we know the semantics of the attributes. If I have a table of employees and I have attributes, there is a name, date of birth, salary, I don't know, role, days of vacation, I don't know what could be in the table, then the user that works with the data, with the database, with the table, which is some database operator, can formulate a query that is based on the attribute. So that's why we have the SQL query language, and the SQL query language is basically based on the attributes. So we are, and of course, the tables and the attributes. So the users are supposed to know the semantics and the structure of the data. So this is the easy case of relational databases. Then we could move to full text databases, what we have discussed the previous lectures, and there the situation is a bit worse, because we still have quite strong semantics, because we still have the natural language where the keywords are expressed in. So if we have a text that is normal text in English or in some language, we can understand the individual keywords, because these keywords are words in the natural language. So we know the semantics because of this shared vocabulary that is in natural language. But we basically lose the structure, because we don't have nicely shaped table of attributes and everything, but we have just a plain sequence of words. So that's why the texts are already classified as unstructured data, because of this loose structure. It's just a plain sequence of words. Of course, we can extract some linguistic structure out of that. We have sentences and paragraphs and so on, but otherwise we don't have the structure of the data that is inside the text itself. So if the text is a book and there are some scenes in the book and some belletry book, we don't recognize it just from the sequence of words. We must extract it some other way. But this is not the case of relational data. So full text retrieval is worse, but still not so bad because of the strong semantics of keywords. And the worst is the multimedia data, because we don't have good structure. We just have pixels in images or just sound samples in the digitized sound wave. And we don't have any semantics, because semantics that is connected to pixels is no semantics. That's semantic only that there is a color, and this is too low level semantics. So we basically don't have any structure and any semantics other than that is necessary for storing this data or reproducing this data. We can store it as a file or stream it as a video stream and display it on display, and that's it. Otherwise we must for the purpose of search, we must somehow develop something else. So we cannot use directly the data, the pixels. This is completely different from relational databases, because we already get the data and we can directly query the data based on what we already have. This is not the case of multimedia. Okay, and now we go slowly to the point, and the point is content-based search. And so if we don't have any meaningful context or annotation, what's left? So we have just the raw content, so the images, for example, and then we need to resort to a method that extracts features from the raw content and search based on these extracted features, and this is called the content-based search. And it doesn't matter if it's image or video or audio, basically the raw content. And it could be also suitable in case that we have annotation, but this annotation is not perfect, is incomplete and subjective and so on. So even in these cases, we might have content-based search as an additional way of searching. And to be not confused, of course, that in the content of multimedia there is finally some structure and semantics, but it must be revealed, or it must be extracted. Of course, if I have a picture of a dog, I have a very strong semantics because there is dog, and also structure because the dog is a segment in the image and so on. But this is not stored in the data itself. It must be revealed or interpreted or extracted out of the data. And this is the subject of the field of multimedia retrieval. So what we want to achieve is some transformation from the unstructured data object. For example, I have a photograph of sunset, which is basically a lot of pixels, let's say 5 megabytes of pixels, and I want to transform this raw content into some description that is more compact, but at the same time is more semantic. So we condense raw content into high-level description. So in this case, it could be transforming 5 megabytes of pixels into just 6 bytes, the word sunset. And this is if this was a lossy compression, that would be terrible performance, because this is very drastic reduction of the information from 5 megabytes to 6 bytes, and completely is not reproducible back from sunset to 5 megabytes. But this is not the task of feature extraction. In feature extraction, we want to extract some useful information for search, and in this case, the keyword sunset is perfectly good. Of course, it is heavily reducing the content to just one word. I could, for example, be interested on what kind of sunset, if it's sunset in ocean or in mountains or whatever. I only have this word sunset, but this is some allowed loss that is basically allowed in this process, because I need to simplify the model and make it more semantic, and this is what I want to do. This is of course extreme case. I basically will not end up with keyword when doing feature extraction. I will get some features, statistical features, for example color features, something, but it's the same principle. I reduce the amount of data that has no structure to something that is smaller and has better structure and better semantics. And for this reducing and extraction of features from content, there was it was empirically proved that the best model for searching any unstructured data is the similarity search model, because the similarity search model is quite versatile and extensible and could be used for any kind of data, and so it serves as a nice framework for content-based search. And in this similarity search paradigm, we basically need two components. The first component is the feature extraction procedure and the model, feature model, and the descriptor model. And here we basically, the procedure is responsible for transforming the input data, in this case images, into some descriptors. So even in this case, we get actually some structure from non-structured data. So these data objects are not structured in the sense I was talking about, but we get some descriptors that basically store in a structured form the features of this data. And we are already in, again, structured data model. But it is not the same case as in relational databases, because it could be viewed as a relational database now. If these descriptors are just vectors, which could be, and we have a number of descriptors for a number of data objects, and every descriptor is a vector, for example, then this could be viewed as a matrix, and the matrix is a basically table, so it's a relation, so we could view a set of descriptors as a relational as a table. But it's not the case, because in relational databases, as I said, we have basically public or understandable attributes that are directly used in the query language. But this is not case of features that are extracted out of data, out of multimedia data, because this structure is hidden to the end user, because these are some features that are probably technical features, maybe some statistics on colors and so on, and these are not designed for the interface with to be used in the interface with user. So we cannot directly use these features within these descriptors to the user, and therefore we need a second component, and this is similarity function. So instead of exhibiting these features to the user, we don't exhibit these features, but we define a similarity function that takes pair of these descriptors and computes a number that is interpreted as a similarity of the original objects. So for example, if I have a descriptor for apple and a descriptor for pear, I compute from these two descriptors a number, and this number is interpreted as a similarity of apple and pear. So this is what I get by similarity function, and this is much more comfortable for end users, and because user can understand if a value is larger or smaller, so what is more similar, less similar, and is completely uh, isolated from what's inside these descriptors, because the user can only view the similarity, and even this similarity scores could be hidden from the user, because we only can provide the user a ranking as the user is used to in Google in the ranking. So if this is a query and this is the match to the query, or this is the first object in the ranking, so the user only sees the ranking. So this is the best match, for example. There is nothing needed from the model to be exhibited to the user, which is completely different situation than in relation databases. Let me remind that this is just a general framework, and there is not any specific prescription how these descriptors should look like. Okay, it could be vectors, but it could be anything else. And there is also no requirement on this similarity function. So this similarity function is just a pairwise function that takes pair of these descriptors and computes some number. That's it. So everything else is a subject of domain-specific implementation under the similarity search model. And now, how can we use this for querying? Because we cannot, as I said, use the features of the descriptors, because these are hidden. So we cannot use them in something like SQL. We could use only the two components of the similarity search model, so the feature extraction and the similarity measure. And based on these two simple components, we can define a concept of query by example, where the query is defined by an example object. So this is the same type of object as we have objects in the database. So that's why it's example. We have, of course, the descriptor of this object. So we have descriptor of the example, and then we can use the similarity measure to compute all of the scores between the descriptor Q of the example objects to all of the descriptors of objects that are stored in the database. And we get the final ranking. So we again have some ranking. So we could maybe use it for some other re-ranking and so on. We have discussed earlier. So we have another mechanism how to produce some ranking, this time based on multimedia query by example query. And if we have this ranking, we of course need to somehow limit the ranking to the result that could user be displayed that could be displayed to the user, and therefore we need to define some extent of the ranking to be returned to the user. And this definition of extent could be done basically by two basic means, and the first is the range query, and the second is the k-nearest neighbor query. In the range query, it's easier. It basically takes from the ordering, from the ranking, the top objects that all are above some similarity threshold. So we directly define similarity threshold that needs to be exceeded in order to return these objects to the user. So this is range query. The k-nearest neighbor query is simpler because it just says no matter of how the similarity scores look like, just return me k of the most similar objects to the user. Of course, this is more user-friendly, and this is more for experienced users, but there are pros and cons for both of these types of queries. Let's have an example. Here we have some query object. This is the example that is taken from the same database or could be downloaded from completely different source. But what we need to do is to compute the similarity of the query objects to all of the other objects in the database, and basically returning the ranking of the objects that are scoring the best. So we get ranking of objects from the database, and based on the type of the query, we can get different prefixes of this ranking. So for 3 nearest neighbors query, we get these 3 objects, these 3 docs. and that's it. In case of range query, we define that the threshold for the similarity is 0.5. So we need to retrieve basically all of the objects that score at least 0.5. So we have 4 of them. We have this one, this one, this one, and this one is 0.6. And the fifth is not, because it's just 0.4. So in case of range query, we get 4 objects. And the difference between range query and k-nearest neighbor query is in the confidence of the user or the comfort of the user. The k-nearest neighbor query, this is the Google-like query, where we get the first 10 results on the Google page of results. And this is easy to basically define, because we just know ahead that we get 10 results. But we don't know if 10 is enough. So that's the problem of k-nearest neighbors. If we realize this is connected to the problem of precision and recall we had in the maybe second lecture. And if we use k-nearest neighbors, we are not guaranteed with the highest possible recall. But in the case of range query, when the user is confident about this threshold, because the user knows the semantics of the similarity and can really guarantee that what is below 0.5 really is not relevant, like this one, then the user basically gets 100% recall, because basically he differs this confidence, the query differs the confidence to the user, and basically we get something like Boolean query, but sorted, because everything that is beyond 0.5 is relevant, and what is not is not. So we get 100% recall. In case of k-NN query, we don't have this assurance, because we don't know if it's not, enough or more. In case of Google, there is some hybrid solution that basically gets the best properties from both of these approaches. In Google, we can get first 10 results, and then if we are not satisfied, we can click on next 10 results, and so on. So we can incrementally do 10 nearest neighbor, next 10 nearest neighbor search until we are satisfied. So this is something like extending the KNN to interactive KNN, and basically we are getting to better recall, and still do not use this range query thresholding, because the threshold is really supposed to be defined by expert who knows if 0.5 is good or bad. Okay, so this is the basic example of similarity searches. And now a bit of formalization. So if we want to formalize the similarity model, then we need the function for the feature extraction. Let it be a function E that transform instances from universe X to universe U, where the universe X is the universe of all the original data. So for example, images, the pixel matrices, and the universe U is the universe of the descriptors that basically represent then the descriptions of these objects from X. So we then have basically two sets. One is subset of X, one is subset of U. So this is the origin database D, and this is the descriptor database S. And this is basically the sets we work with. And the second is the similarity function. So as I said, it's a pairwise function that takes a pair of descriptors from U and computes a real score from a real number. And here we of course need to distinguish if this score is taken as a similarity score or dissimilarity or distance score. The similarity score means that the higher the better. This is the case of cosine similarity we already discussed, but it is often more convenient to take the inverse formulation as a distance function, not similarity but dissimilarity, because then we can basically geometrize the problem and view the query as a ball in a space, and we are searching searching the vicinity of a query object with a point, which is a point in the space, and the threshold in the range query is basically a radius. So we are searching for inside of a ball, for query ball. So for this reason, it's better to think about the similarity function as distance function. So meaning what smaller number means closer, distance means higher similarity. And the query types, query by example types, we already shown by the examples, could be formalized like this. The range query is very easy. It's defined like the example q and the query radius r. Now we are in the way of distance, not similarity. And the result is all of the objects from S, which is the descriptor database, where the distance delta from the example to the object from S is smaller or equal to R. So all of the objects that are within the query ball in the space are part of the query result. So this is easy. The key nearest neighbor query is a bit more complicated, as we see, but it's still easy. It just says the extent is not the extent is k. It's not the radius, and it just says the size of the result is k. And but we need to get nearest neighbor. So we get a subset C of the database that has size k, because we want k nearest neighbor. So the result is of size k. And all of the objects from C are closer to Q than are objects outside of the C. So this is basically a condition that must be satisfied, and that's it. So we are guaranteed that C contains the closest neighbors to nearest neighbors to Q. And now this was basically the framework for any domain and any usage, but how we actually get descriptors of multimedia objects. Of course, we must somehow process the very raw information, like the pixels in images, and this basically leads to extraction of some very low-level features, which are the basic building blocks. For example, we can count the number of colors, so we can extract some local small fragments, and there are many different ways of feature extraction. And this often provides just local information, so it's low level and even local. And we use here the techniques from computer vision, and this is really close to the technology of image processing, for example, and also from psychology, because we need to extract stimuli, which is something connected with human cognition. So we must of course extract from the data something that is that mimics the stimuli of the user, that really sees the nature of the data. So that's why it's also connected to cognitive psychology. And then if we have the building blocks of the low-level features, we can construct some descriptor that is condensed and basically needs to somehow aggregate these low-level features, that are maybe many of them, to some concise and expressive enough descriptor. And this is another expertise. There are techniques from multimedia retrieval, also other machine learning and classification, data exploration, and so on. So we need to assemble some descriptor that needs to be quite small. So we cannot do descriptor for 5 megabyte image and have 5 gigabyte descriptor. So we need really something that is small and expressive enough. There is one activity that led to standardization, and it's called MPEG-7. So the standardization group MPEG quite a long time ago, 22 years ago, basically launched a project MPEG-7, which is a standard for description of audiovisual content and allowed to basically represent multimedia data out of proprietary applications. Of course, this is always the role of standardization, because as in the case of of semantic web, we had there the standards of W3C, the link data, RDF, and so on. And of course, this was not the only contribution to semantic web technologies. We have already semantic web within the applications on the web. Of course, we have quite strong semantics and structure within Facebook, because we have there the entities like user, post, and so on. But this is application-specific semantics that cannot be exported outside. And the same with multimedia. We can have applications like again Facebook or YouTube or something that somehow can extract features and represent for the limited application uses within the application. But if we want to work with the data independently on the application, we need something else. We need some standard, and the MPEG-7 is such a standard, such as the RDF was in semantic web technologies. So MPEG-7 is a standard for description of audiovisual information. Okay, but what's the descriptor we already saw as a black box? What is the possible structure of the descriptors, regardless of any standard? So on the mathematical level, the descriptors could be of several kinds. Of course, the most useful mathematical structure for descriptor is vector. So we can characterize an object with a bunch of numbers, where each number is associated with some dimension. So we have multi-dimensional vector, and basically these numbers are the values within the features that are defined by the dimensions. We can also view vector in some cases as histogram. Histogram again is a vector of numbers, but in case of histogram we prefer to visualize these numbers by these bars, because then we can also visualize the properties of the dimensions. So for example, if we use vector for representation of color histogram, then it is quite natural to visualize the proportion as a bar, and the bar is in the specific color. So for example, I know that I have an image, and the largest proportion of colors in this image is this blue, and a bit less, and it's this violet blue, and even less is this purple, and so on. So I can see using the histogram the properties. But what is more important is that the histogram expects that the dimensions are somehow correlated. So the index of the dimension does mean something. So if I have dimension, I don't know, here it is 1, 2, 3, 4, 5, 6, 7, and 6. So 7 and 6 are somehow related, and we can see they are related. They are almost the same color. So it does matter. The order of the dimension does matter. They are correlated by their semantics. We also can aggregate the dimensions in the histogram to get the small number of the dimension, but basically we only merge semantically similar features, like two versions of blue. But this cannot be done generally for any vectors, because in vectors where we don't expect correlated dimensions, we just have very independent dimensions, and we cannot just merge the neighboring dimensions, because this is something completely else than this. For example, this is if this is a descriptor of a human, this could be a height, and this could be, for example, salary. I cannot merge height of person with salary. That doesn't make sense. But here it makes sense. So it also makes sense to represent some vectors as histograms. Okay, so that's a quite long discussion about vectors. So a part of vectors, we can use something that is more general, because this vector structure basically expects that we create kind of canonization for the description, because if we set the dimensionality to some number and the dimensions are connected with some features, here with some colors, then we basically created some system of mapping quantity of features to the dimensions within the images. But this could not be always possible. So in this case, that we cannot canonize or cannot create some system for features, the dimensions, we just must allow to just provide container for arbitrary features. And this is the case. For example, I can identify some features within an image or within some object and just put it in the set. A set is just a container. It doesn't matter on the order of the elements within the set. They are just placed there in arbitrary order. And also there is a different size of sets between objects. So one image, for example, could be described by many of these bubbles, and other image could be described by just a few bubbles, because this image was more complex than another one. For example, if I have a very trivial image that is only white, I would not have, I'll need not so many bubbles to express so many features, because it's just white. While if I have very complex image of nature, of tree, I don't know, of landscape, then I would need many more features. So that's why sets not only provide unstructured container for features, but also dynamic in size. So that's why sets are really the most general representations for descriptors. But of course, every set needs some internal structure. So this is not it. So with vectors we are done, because maybe we have just these numbers and that's it. But for sets we must further detail how this bubble is represented. So we could have set of vectors, and then so there are substructures within the set. So it's much more complex. And we can also have ordered set, and this is mostly suitable for time series to observe some phenomena in time. So that's why the ordering. So ordering mostly is connected with time. So we have time series. Or if we also consider strings, this is also ordered set, but symbolic. It's not numeric time series, but symbolic time series. And in strings, it's no longer connected with time. It's really order. But it's still ordered set. And again, we have two more properties over vectors. Even for the numeric ordered set, we first have correlation with the dimension, as we had correlations here between the neighbors. Here we have correlation in global scale, because it's time. So this is more relevant to this than this is more relevant to this, because it's close in time here, but it's not close in time here. So there is correlation in time. And second feature is that the time series could be differently long. So there is not a restriction on the dimensionality of the time series. Here it is. There must be set fixed dimension. Here we can have different dimensions for different objects. Okay, so this is just the basics about how could the descriptors look like mathematical structures, but how should the similarity functions look like? Of course, they must follow the structure of the descriptors, because they operate with them, so they must be designed for the descriptors. So we cannot just combine them arbitrarily. And for vectors, for example, we could use the well-known family of Minkowski distances, which is a very, very well-known distance. Basically, if we substitute for this P2, we get the Euclidean distance, and Euclidean distance is the distance in our real world. Basically, it could be visualized like this, and of course, it is defined for any number of dimensions. So we have multidimensional Euclidean distance, or generally LP distances, Minkowski distances. And this family of distances, as we can see from the formula, is the distance that is designed for vectors, of course, because it takes the components of the vector, it takes the dimensions from I to D of, if I have two vectors, and I do subtraction of the same dimension of two vectors, and I subtract, and then I do power, and then I sum it, and then I do finally the square root or the p root. And as we can see, this naturally is a distance that does not expect or does not support correlation between dimensions. So it assumes independent dimension. Why? Because it is very simple distance function. It only goes through the two vectors and only measures the difference in the coordinates of the two vectors in the same dimension. It doesn't look forward or back or afterwards. It just takes the ith dimension in both of the vectors. So that's why it is suitable distance function only for vectors that are also supposed to have independent dimension. If we have different assumptions, for example, we have vectors that are basically histograms of colors where different dimensions can have different relations between each other, then this is not so good solution for using, because we can have, for example, if I get back to this example, I have some proportion of this blue and some proportion of this blue, and in another object I can have the opposite. So more of this blue and less of this blue. And if I compare these two images based on these histograms using the L2 Euclidean function, then these two dimensions really appear as completely independent dimensions, and they will result in large difference in this dimension and large difference in this dimension, and this would be interpreted as not so similar objects. But in fact, because these dimensions are correlated, in fact the images could be not completely the same, but very similar. And just because of the Minkowski distance that didn't basically view these two dimensions similarly, it will be misinterpreted as not similar objects. So that's why it must be taken carefully, and Minkowski distances are really for independent vectors. Cosine distance, it's similar, it's what we already had. It measures the angle between the vectors. Again, this expects the independent dimensions. But if we have histograms where the dimensions are correlated, it's better to take quadratic form distance, because this allows to set correlations between individual dimensions in this correlation matrix M. And this is better way how to measure distances between, for example, color histograms, because it really is more robust with respect, for example, to matching similar colors. This is the geometric interpretation. There are correlations, so in the geometry it leads to arbitrarily rotated ellipsoid. For the sets, or for the adaptive variable sized and variable structured descriptors, we can use also adaptive distances. One of them is called signature quadratic form distance, basically some generalization of the quadratic form distance that was originally just for histograms, but signature quadratic form distance is for general sets, but just because we can concatenate the two sets, and there is some trick with this, but basically this allows us to match two sets. Another that is quite famous distance basically originates from is another version of the so-called transportation problem. In transportation problem we have two distributions of Earth of landscape. Let's consider this histogram as a landscape, really landscape. And this is another landscape. And the transportation problem is to find a solution of this redistributing the mass of this landscape to become this landscape with the least possible amount of work. And the optimal solution basically gets us also the amount of work is the distance, because the distance is measured as the cost of transforming one distribution to other distribution, and the earth mover distance basically computes this. So this is the cheapest possible work plan to distribute this distribution into this distribution, and the work itself, the amount of the work, that's the distance basically. So again, the landscape with itself, there is zero cost, and if it's completely different, there is much more work. Another set distance is a Hausdorff distance, and it is quite practical for applications. Consider or imagine these points. We have these red dots and blue dots, and imagine that the red dots come from one fingerprint and the blue dots come from other fingerprint of human hand, so for biometric identification. And if we just overlap these two sets, we can measure the similarity of the two sets of dots by the Hausdorff distance. For example, like this. In Hausdorff distance, we are basically computing for each element of one set. For example, for each red dot, we are searching for the closest blue dot, and from all of these pairs of closest red and blue dot, we take the largest one. And we also do it from the other direction. So for all blue dots, we search the closest red dot and again take the largest one, and then from these two distances we take the maximum, the larger one. So this is basically the result, and it says these two sets of dots based on Hausdorff distance are distant this distance. So this basic distance between the two dots. And this is an example of conservative distance function, because it really is careful in favoring similarity. It favors dissimilarity because it emphasized, or the final score is the largest distance here, and this is basically good for the biometric purposes, because if we want to really identify two fingerprints as the fingerprint from one person, we must be really careful because it could have critical consequences. That's why I was talking about critical and non-critical applications at the beginning. And here we get some very careful value that could be enough or not, depends on the criteria of the system then, because it could have serious consequences to identify somebody as a criminal or something. So Hausdorff distance. For sequence distances, time series or strings, we have a specific class of algorithms that are called alignment algorithms and are computed using so-called dynamic programming mostly. And the most famous algorithm or distance for strings is the edit distance. The edit distance measures the number of basic operations, replacing, inserting and deleting of a character to convert one string into another string. And this could be done by the dynamic programming, and I can see this as an alignment, because alignment gives me the recipe how to convert this string into the other string. And in the recipe, the number of non-matches, which is here illustrated as the vertical or horizontal edges, is basically the final edit distance. So in this case, I have edit distance of 4 because I have this insertion, deletion, deletion, insertions. I have 4 of them. The diagonal is match, so there is not an operation. No. So I have this edit distance, and edit distance and other string matching distances are heavily used not only in simple applications like spell checkers and so on, but very frequently in bioinformatic applications, where even here we see that this is not normal string, this is DNA string, and again this is another DNA string. So in the biometric bioinformatic applications, they are not just these eddy distances, they are trivial, but they are dedicated alignment algorithms for bioinformatic purposes that also involve other information than just strings. There are some chemical properties and penalizations for introducing gaps into the alignment and many other features. So this is strings. For numeric time series, there is popular so-called dynamic time warping distance, and this distance basically is a generalization of Euclidean distance, but has some nice properties, because it not only can take two vectors or two time series of different dimensions, this one is longer than this one, but it also can align the elements of the two time series in an optimal way. So instead of aligning the ith dimension of this one with I dimension of this one, what would be the case of Euclidean distance, and it would just sum these differences just vertical, and this would be ignored probably, because Euclidean distance can take only vectors of the same dimension. Here in the dynamic time warping distance, we can see that the alignment was optimal in a way that it matched this peak with this peak, and this is basically what we wanted to obtain, because probably this is some sampling, some phenomena, and but we have shorter period of the sampling, so it began later, so the peak began earlier than in this case, but this is not a reason to not consider these two time series as very similar. So this is the property of time warping distance that gives us this kind of robustness, and these two time series are identified as similar. Okay, now some applications. If we have the idea how to represent descriptors and how to compute the distances, now what are the applications? So if we want to model features or descriptors for images to provide retrieval, we can model some global features out of images. So what is very basic descriptor for images could be the MPEG-7 descriptor called scalable color, and it basically what it represents is a basic color histogram. It's nothing very special. If I take histogram of color, everybody who knows Photoshop knows what's color histogram. I have three histograms per the color channel, red, green, blue, and the scalable color basically does a compression to this. So it's basically compact form of this three-layer histogram or three-color histogram. So that's scalable color. It only results in 60 to 128 dimensional histogram out of this much larger histogram that has, I don't know, 3 times 256 or even more levels of each of the color channel. And then on this quite small dimensional vector that is histogram, the L1 distance is used. So the Minkowski distance with p equal to 1 is used, and it could be the images could be compared by the similarity of their descriptors constructed as scalable color. So this is something that is very basic descriptor for images. Probably cannot be easier or simpler descriptor for color images that is somehow meaningful. But what I want to show here is another descriptor that is not so obviously or not so obvious, and this color it's called color structure, and it nicely demonstrates what is descriptiveness of descriptor. So I don't want descriptor to be good representation of the original object that keeps all of the properties. So I don't want a compression of the original object into descriptor. I just want to keep the descriptor to be as expressive as possible in the meaning that it will distinguish between two different images in the feature that needs to be distinguishing between them. So if we want to distinguish between these two images, we can see that in this first image there is something called high color structure. High color structure means we have some nicely shaped larger shapes here, or larger objects, and here we have low color structure. That means we have some kind of noise or some broken images and broken objects, and this is more like some noise, right? And if we want to distinguish between these objects, we need to somehow compute number that distinguishes these two. And how this could be done? And let me say that there is exactly the same number of color pixels here and here. The difference is just the color structure. There is the same quantity but different structure. So if we just compute the number of brown dots, is the same here and here, but the color structure is different. So how we can compute this? And the method is very simple. We take this window 8 times m, it's called structuring element, and here it's only 3 by 3, but in reality it's 8 by 8. And we basically traverse all of the positions that we could achieve using this window, using this structuring element. And when moving to every position, we look inside to the structuring element, and if there is at least one color pixel within the mask, we increment a number by 1, a counter by 1. And we do move this structuring element through all of the positions here, incrementing every time there is at least one color pixel, and we get some number. And if we do the same for this image and this image, then we get larger number here, because the probability that the structuring element will see at least one pixel of the color inside is here larger, because it's more evenly distributed here. We can see there is not much empty space, there is always something, but here we have large patches of completely white. So there is some chance that in some portions of this image, this structuring element will be completely white and will not be incrementing the counter. So, and this is it. It distinguishes by some number that is completely artificial. It just says here some small number and high number. It has completely measureless numbers. It just says this is different than this because the number here is much larger than this one. And this is basically the essence of descriptiveness of descriptor. It does not have to mean anything. The numbers are just numbers, but it needs to distinguish between two different properties of the images. And just to be complete, this color structure doesn't measure number of pixels in monochromatic images because this is just one color, but this is just a cut out of images for one particular color. And we could of course make so many cuts, how many colors there is. So we can compute this using the structure element, the counter for each particular color, and put all of the resulting numbers into, again, a histogram for all of each, for every color. We have a bin here, and we do the same for all of the pixels of that color. All of the other pixels are regarded as 0. And so we create this histogram. And then we can compare, again, two images based on two histograms of this color structure, use the L1 distance for that, and can use it as a descriptor. Of course, we can combine these descriptors. We get so-called multimodal description. I will talk about multimodal retrieval later on some later lecture. Okay, so this was global features. We can also use local features which were used originally or are used in computer vision for detection of objects. And the most prominent local feature that could be detected in images is so-called SIFT descriptor. And it's based on detection of so-called interest points. Interest point, it is nothing very special. Interest point is a location in image where there is some very unique specific change of contrast in the intensity function. So if I imagine this image in black and white, because it's done not in the color information, it's only done it's only computed using the intensity or the intensity function. And if there is some very specific fingerprint, then it's interest point. And SIFTs are basically representations of such interest points. They are also robust and invariant with respect to rotation, scale, and so on, and basically represent not globally the image, but every SIFT is one of these bubbles, as we can see here. It's just visualization of the SIFT. Is basically not localized, or the SIFT itself then doesn't belong to the specific location. It just originated from this location. So it's then without any coordinates. And we have from this image we can see that we have a few hundreds of SIFTs, and we can then work with the SIFTs as it would be the final product of the feature extraction, or we could condense them into a more compact descriptor. As I said in the beginning, this is the first phase of detecting local features, and the second phase we can compose a more complex descriptor out of these local features. And then if we compose these SIFTs into a set of local features, and we have two images, in this case this is the Eiffel Tower, and we have these two sets of SIFTs, one set of SIFTs, second set of SIFTs, and use, for example, something based on Hausdorff distance, then we can basically obtain this kind of matching SIFTs from the one set to the other set, and basically can identify that these two images contain the same objects. Basically they are not the same images, of course, but contain the same object. That's why also SIFTs are used for object detection, and they are not measuring similarity. They basically just detect objects, but it could be interpreted as similarity. The last example we discuss in the domain of image retrieval is image retrieval and object detection using deep learning, which is nowadays a very hot area of research. And here we basically can obtain either global descriptors or local detections, for example, but I only show here two possibilities. Deep learning can do much more of these representations. So in the very basic settings, we have a convolutional network. On the input of the network goes the input image that we want to do the extraction from the image, and this network is a basically pre-trained model using some general imagery. This is for larger discussion, but what we obtain is, during the inference in the network, we can not only get the classification, which is the main purpose of convolutional networks, but we can even take some activation on some layer of the network and use it as a descriptor. So for this purpose, we have this layer, which is 4096 neurons. Basically, it's this high-dimensional vector for every activation. We put an image here and obtain high-dimensional vector that is a representation of that image in this basically deep features. It's called deep features because they are trained from the very low-level features like this one. There are some edges and blobs, and how it goes through the network, the features get more and more high level. So we get two textures here, then we get to objects here, and then we get to complete scenes here, or object parts and on complete objects. And this is something that aggregates everything together and represents semantic visual description of images in this case. From the second point of view, we could detect objects. So it's no more detection or extraction of features. It's more high level. It's basically detection of objects in images. So in this case, we have a video stream or just video frame, and we detected objects of type person and objects of type car or tram, and basically we could view this as a feature extraction, of course, but it's more than that. It's really detection of objects, because these features are already so semantic that they make sense to users like SQL users. So we can really do, for example, aggregations of number of people on street or something like that. So this is beyond the simple feature extraction. But these all magics could be done with deep learning. In the domain of shape retrieval, we could use nice example where the shape could be represented by time series. This is very funny, but surprisingly working example of feature extraction, where we expect skulls pictures like this. We have skulls, human skulls or monkey or animal skulls that are, of course, from profile, so they are normalized somehow, they are isolated on white and so on. And if all the data are in this nice form, we can basically extract contour out of every skull like this. So we have this shape. And the shape could be furthermore extracted for features by computing the centroid of the shape, because it's closed polygon, it's easy to compute a centroid. And then when computing the distance from the centroid to all to the shape in all possible angles, going, for example, starting here and going counterclockwise here, so we get basically time series, which basically is some unwrapping of the original polygon. So if we can see, we basically still have preserved the features of the original polygon. So there is a nose here, it's still here. There is a chin here, it's still here. So we get some almost equivalent representation of this polygon to a time series. And then we are in the domain of time series, and okay, we already defined that distance for time series. In this case, it's for 2 gorillas. We get the time series for the gorillas, for 1 gorilla, for second, and do the alignment using the dynamic time warping distance. And the resulting distance says if how similar these gorillas or their skulls are. So this is nice example how the dynamic time warping distance could be used. There could be also different distance used. Instead of dynamic time warping distance, we could use so-called longer common subsequence for another use case. In this use case, we don't have gorillas, but we have we have just human skull, and this is another human skull, but this is taken from some archaeological site, and it's broken. There is missing a nose, and if we use just the dynamic time warping distance, we would get quite pathologic alignment of these two time series, because here we can see we have the nose, so it is here, but because it's broken, this skull is missing the nose, there will not be the nose, so there will be completely different shape. And using the dynamic time warping distance, these two cannot be aligned because they look differently, so there will be produced some very pathological alignment here, and the whole matching would basically misclassify the similarity of these two, and the dynamic time working distance would compute a large number saying that these two are not similar. But in case of longest common subsequence, which basically does what is the name, so longest common subsequence. So it basically counts only the subsequences that are common. So they are not common. The sequences are not common in the part of the nose. So this part is ignored because it's not common, and the only part that is involved in measuring the distance is the rest. So everything else than the noses. So in this case, the alignment would be much more precise and matching everything except the nose. And so in this case, the two skulls would be classified as very similar up to the missing nose, which was the intent. So this was these experiments were performed by Professor Iman Keok from University of California, and he's famous by using time series for feature extraction of everything. Now we get to audio retrieval, and the basic of any feature extraction in audio retrieval is the waveform spectral information, or the transformation from the time domain to the frequency domain. So what is commonly done in feature extraction in audio is basically splitting the audio signal by windows into very short pieces, and then transformation using the Fourier transformation into the spectrum. And basically this is the basic building block for many of audio descriptors. Again, there are defined audio descriptors in MPEG-7 standard. There is 17 of them. It's a huge number, but I only show two of them. One of them is called audio spectrum envelope, and basically what it does is it creates. Basically, it's also interesting. It creates picture out of music. So we are converting music into picture. How it's done? So this is the original music signal. Probably everybody knows. This is basically the function that could be used to move with the membrane of the earphones or something. And we need to do the feature extraction. And the feature extraction is done in the way that it's split into very short time frames, and each time frame is transformed using Fourier transformation into the spectrum. And the spectrum is basically a vector of coefficients of sine functions of various frequencies, and these coefficients are then taken as a vector and visualized as a pixel column in this image for the particular time frame. So every time frame has a one pixel column allocated here, and for every time frame one vector is extracted from the respective time frame, and it's visualized as a grayscale image here. So if the frequency is highly present in the spectrum, then it's more black. If it's not there, it's white. So we get this black and white image out of sound, and then we can use this directly as a histogram. But because it's too complex, still we can use it as only as intermediate, not histogram, descriptor. We can use it as an intermediate descriptor and basically convert then this image into another descriptor, but this is a descriptor for images. So we can do a pipeline of transforming data in very different forms. So from music to image, and from image to descriptor, and then just making image retrieval on this. But originally it's on the sound. So this is one way of how to represent audio. If we resort to symbolic representation of music, not any audio, but music retrieval, and use the symbolic representation, that means we are not doing extraction from the audio wave, but from symbolic representation like notes from the score, then we can model nodes, for example, as 3D points. In this case, every node is given its first coordinate in time, so this is time. Second, it is the type, so this is a pause, this is a note of length, and the second and the next is the pitch, or other way. This is pitch and this is the type. And this way we can represent basically monophonic melody. So every melody could be transformed into the sequence of three-dimensional points. So we get a time series here, but not time series of numbers, as we were discussing before with the shapes. But here it is time series of three-dimensional points, and then we can match two time series of three-dimensional points to melodies like this. So this is one series, this is another series, and it's visualized using the coordinates, of course. And the third coordinate is the thickness of the dot. So we have these two as x and y, and the third one is the thickness of the dot. And using the so-called proportional transportation distance, which is something similar to earth move distance, we can basically measure the distance. We do the transportation problem for this, from this distribution of nodes into this distribution of nodes. We can see that it's very similar. We get some overall distance 0.7, which is probably stands for similar melodies. So it could be returned for this query, it could return this result, for example. So this is another application of melody. And now we go to the last part, and this is more performance oriented part, more database oriented part. So we want all of these models implement and run on web scale, of course, because we are searching web, or at least at the largest scale as is possible. So we need to power all of the components in the similarity search by some databases, or by some hardware. So in case of feature extraction, that's really expensive, because we use in the feature extractions all of these deep networks and SIFT extraction and all of this. But it could be first very well parallelizable. So we take the huge database and split it into pieces and delegate it to different machines. And also we can forward the feature extraction even to clients. So instead of processing this on the server side, we can let this to the clients, because clients, when clients upload data, for example, to some social media, they probably are not uploading huge amounts of data, or with at least with comparison to what happens in the cloud of Facebook, for example. So it is not so much overhead to also do the feature extraction in addition to the uploading. So this is quite nice way how to delegate the workload. And as of course it's very parallelizable. So and another point is that these updates and these uploads are in reality much less frequent than querying. So as I said in the beginning, it is expected that on YouTube it is uploaded every minute 500 hours of videos. So it's a huge amount per minute, 500 hours of video. But at the same time, every day YouTube has billions of watches of these videos. So the querying or the access to the data is basically 2 orders of magnitude larger than updates to the data. So it's definitely worth invest time in feature extraction and indexing and this stuff, and for the sake of querying, for the quality of the retrieval, because we are mostly interested in the retrieval. So this is feature extraction. Then the similarity function is also computationally expensive, and it could be solved. The complexity of the similarity searches could be could be reduced by indexing, by database indexing. So and this is basically the topic we will take two more lectures, because this is basically database related topic, and it's quite crucial, because this is basically the bottleneck of any searching is of any search engine is the speed of searching. So the similarity indexing and the similarity search as such is basically the critical part, because otherwise it could be very parallelizable and delegated to the clients, but not the searching itself. That must be done by the server. Before we get to indexing, we must also discuss the computational complexities of the distance functions. I have presented many of distance functions. Some of them were very cheap to compute, and some were quite expensive. So the cheapest distance functions, of course, obviously, are the LP distances, cosine measure, and or, for example, a Hamming distance, because as we can observe from the formula of LP distance, for example, it works dimension-wise, so it only accumulates the differences between the dimensions. So it basically takes just n steps, where n is the dimensionality of the, or size basically, of the descriptors. In case of vectors, is dimensionality of the vector. So it has just complexity O(n), so it's cheap. The same cosine measure, the same Hamming measure. A bit more expensive are the more sophisticated distances that compute or work with correlation between dimensions, like the quadratic form distance, because there is a matrix, we multiply matrix with vectors, so it's quadratic. Or there are the alignments. So this is again computed using the dynamic programming, which again is a matrix, so it must be also quadratic. So it's eddy distance, dynamic time distance along some common subsequence, and also the set distances, like the Hausdorff distance, which it is also end-to-end matching, so it's quadratic. And there are even more expensive distances. For example, the tree variant of eddy distance, so-called tree eddy distance, is polynomial, is larger than quadratic, and the most expensive in this case is, for example, the earth mover distance, that in the unconstrained form could take really exponential complexity, which is unfeasible basically in reality. It could be optimized to polynomial, but in the unconstrained form, it's exponential. So this also must be taken into account when it comes to the performance of similarity search, to indexing, and this stuff. Well, regardless of different complexity of the distance functions, it is generally assumed that the distance function delta, that's supposed to be the component of the similarity search, is computationally expensive. So it is assumed that most of the runtime that is spent on similarity search, on answering the query, is spent within the computation of these delta scores. So therefore, the objective then is to minimize the number of distance computation as large as possible. So let's minimize these explicit computations. Of course, this is not always true, that there is the runtime spent in this delta function is the largest component of the whole real time, but it's mostly the case when the complexity is, for example, quadratic. Then it's true. But if it's linear, if you have a Euclidean function, this probably will not be true. So in such a case of low complex distance functions, we must also take other concepts into account, such as the traditional IOs, so this meaning accesses to disk, which is the traditional cost measure for database systems. So of course there are multiple criteria for optimizing the performance, not just computation of the delta. But In the in the theory, the dominating factor for minimizing the cost is the number of distance computations. And the way how to obtain this is, and at the same time to keep the model still generic and extensible, is to use the metric space model of indexing, where the distance delta is supposed to satisfy the metric properties. So if it is so, then it is general, because we still do not restrict this delta to any specific formula or algorithm or anything. It only must be a metric distance. So it is still a black box, and also the descriptors are black box because they are connected together. So it is a good trade-off. And what must be satisfied is that the metric postulates must be satisfied by the delta function. So meaning the four axioms: reflexivity, positivity, symmetry, triangle, inequality. And these properties allow us to take the data space, the database, and partition the database so that during the query execution, not the whole data set must be traversed, and all of the distances must be computed to the query object. And this is done using so-called metric index, and this index is used as any other database index, but in a specific way for the task of similarity search. And all of this then results, of course, in efficient search. So there is a task. The overall goal is to speed up the search, nothing else. And the principle for speeding up the search using the metric space model and generally similarity search is to basically trade the computation of expensive function delta for much cheaper computation of some lower bound distance function of delta. And of course this is very difficult to achieve for all the cases. But the principle is like this. Consider we have a query ball, so we have a query example Q. We have the range query, so we have the radius R here. So what we are trying to achieve is to filter out everything that is outside of the query ball the cheapest as possible. And because every query is reasonable only if majority of the data is filtered out, and only a small fraction of the database is actually inside the query ball, it is quite reasonable mechanism to construct a lower bound that is much cheaper than computing the actual distance. Because in this case, I can zoom in. I want to avoid computing this distance qx with delta, and instead I am able to do some other computation, and the computation is this green distance, which is the lower bound distance to the red one. And how can I do that? As depicted here, I can pre-compute, and this is the in the phase of the indexing. I can pre-compute distances from X, which is database object, one of the millions of database objects that I want to exclude from the search. The distance from X to some object P, that is called pivot, and storing these distances between all of these objects X to this one object P in the database. So I have these distances pre-computed in index. And at the query time, I compute the distance between Q and P. And once I have these two distances, QP and PX, then I can use them to compute basically the lower bound as a subtraction, as the difference of these two distances in an absolute value, and I get this green one. And because this is guaranteed as the lower bound, and the lower bound is still larger than this radius R, then I can safely exclude this object X from search, because if this is guaranteed as lower bound, then the actual distance would be even larger. So it would be even farther from Q than just this lower bound. So this is the basic principle behind every metric index, and all of these metric indexes basically somehow use this mechanism. Also, you might ask, how can I benefit from sparing this computation that doesn't happen when I need two more computations, this one and this one? Well, yes, that's true, but as I said, this is pre-computed beforehand. So this is the phase of indexing, and as I supposed the queries are much more frequent than the updates, then the computations of all of these indexes will pay off and will amortize with the time because I query much often than I index. So this is pre-computed in index, and this is not pre-computed because this is dependent on Q. So I must compute it this distance every time a query is issued. But instead of computing millions of these distances qx, because this is just one instance of database object, and I need to really exclude many of them from search, I will compute only a few distances, this qp, because I don't have millions of objects p. I have just one of object e, or a few. I can have more of them, but a constant number. But this is a parameter. This is the size of the database. So there is millions of objects here and just one object over here. So what I am trading is 1 million of computations qx for just one computations of qp, and I get the lower bound, and hopefully the lower bound is large enough to filter out this from search. Of course, this is not always true. It depends on the pivot p. I can have very bad pivot that is not here, but it's for example here, and then these two distances would lead to zero lower bound, and I would not filter out anything because this green would be zero. It would be the x would be out, but the green one would be zero, so I would not filter it, and I must compute this distance. So that's bad, and that's also why I use more than just one pivot, because hopefully one of the pivots would be as good as this one, so producing large enough lower bound to be able to filter out this object x from search. Okay. I will not talk about the individual metric indexes. They are also called metric access method generally, but I only say a few properties. Of course, as I said, these are indexes. They are supposed to speed up search in metric spaces in the similarity search scenario under metric space model. So there is supposed to be built index like this, and this index then helps when querying to navigate to the partitions of the database that is relevant to the query. So not to traverse all of the data sequentially, but to navigate the query just to relevant partitions, and this is the way how the query is speeded up. Of course, we take into account also the construction cost. It again could be more expensive or less expensive. But depends, and as I said, these construction costs are supposed to be amortized by very much more frequent querying than updates to the index. All of them, as I said, all of these indexes for metric space model use this trick with the lower bounding, as discussed in the previous slide. And they only differ in some secondary designs. So basically, when it comes to the very basic principle of filtering data from search, it is done using lower bounding. And the last slide just categorizes the various structural designs of the metric indexes, or generally metric access methods. The very simplest structural design of metric index is just a matrix of distances. It's maybe too generous or too uh, too inappropriate to say a matrix is an index. It's basically a table. They are also called pivot tables, but it's basically, it is an index. It's a very trivial index. It just contains the stored pre-computed distances. So this is one of the easiest, simplest indexes it could be. But a large category of indexes are based on trees, because there is a huge tradition from database systems. There are many trees for from other domains, like B tree for linear ordering, R tree for spatial databases. There are many trees for indexing, and also these designs were used also for in some of course modified way for similarity search. So there are trees, and some of them are hierarchies of balls, some of them are hierarchies of hyperplane based partitions, and so on. There are also hashed indexes, again inspired by the other indexing methods in databases, and in this case again made to measure to metric space model. There are also hybrid methods that combine many of these designs together, and there are also approaches that basically do not index at all and are more of a nature of caching than offline indexing and online searching for similarity. So all of these indexes will be a subject of next lecture, or the other after the next, and they also could be used for approximate search, which is another lecture. So we basically will continue the next lectures with these database topics on indexing data by similarity. Okay, so this is everything for today.